Okay, so in chapter 3, we introduced the radian measure. Now, radians are another unit for measuring an angle. Whereas degrees are somewhat arbitrary, we just sort of decided one day that there would be 360 degrees in a circle, and so 90 degrees in a right angle. A radian arises more naturally from the geometry of a circle itself. So let's see how radians are defined. So if you have a circle, and say the circle has a radius of r, and you decide to place a length of one radius along the arc of the circle. So in other words, you walked along the arc of the circle exactly a distance of one radius, then the central angle intercepting that arc is exactly a measure of 1 radian. So that is how a radian is defined. You can see that 1 radian is certainly a lot bigger than 1 degree. In fact, the conversion is roughly about 57 degrees for 1 radian. Let's write down its definition. Let's get a look at what 1, 2, and 3 radians look like. So again, if you have a circle of radius r, and you walk a length of r along the arc of that circle, then the central angle has a measure of 1 radian. If instead of walking just one length of the radius, you walked a second length of the radius, so here we have a radius of r and an arc length of 2r, then we would say here theta is equal to 2 radian. And let's see what 3 radians would look like. So that would be 3 times the length of the radius, or 3r. Well, it looks like that's about halfway around the circle. Well, as it turns out, it's not quite halfway around the circle. So halfway around the circle, which is 180 degrees, is a little bit more than 3 radians. So what we are going to need is an exact conversion between radians and degrees so that we can take problems that we understand in degrees and convert directly into radians and vice versa. So in order to do that, we need to see how many radians are in a complete revolution, because we know there are 360 degrees in a complete revolution. So let's recall that the circumference of a circle is given by 2 pi r. This means if you have a circle and it has radius r, and you decide to walk around this circle, then you've covered an arc length of 2 pi r. Okay, so what is this angle going to measure in radians? Well, let's go back here. An arc length of 1r has a theta value of 1 radian. An arc length of 2r has a theta value of 2 radian. An arc length of 3r has a theta value of 3 radian. So an arc length of 2 pi r, which we know would be the entire circumference, would mean that in this case, our theta here has 2 pi radian of measure. But we also know that theta is 360 degrees. Well, this is going to give us our conversion factor. Our conclusion is that 360 degrees is 2 pi radians. We can divide both of those by 2 to get a slightly more convenient conversion. 180 degrees is pi radian. You can see that that's why 3 radians was almost 180 degrees, because 3 is just slightly less than pi. So pi radian would actually be a full 180 degrees. We can also write this as 1 degree being pi divided by 180 radians, or 1 radian being 180 degrees divided by pi. So to convert from degrees to radians, we're going to multiply by pi and divide by 180. And to convert from radians to degrees, we're going to multiply by 180 and divide by pi. Now let's do some examples. Okay, here we have 3 angles that are given in degrees, and let's convert them to radians. So to convert from degrees to radians, we're going to multiply by pi over 180. Okay, so 108 times pi divided by 180. So this fraction reduces because 108 is 3 times 36 and 180 is 5 times 36. So this is 3 pi over 5. And we don't even need to write the word radian. First of all, it's commonly reduced to just rad. However, radians are actually unitless ratios, as we're going to see when we get to application problems. So if you don't write any units at all, it's implied to be a radian. And that's a nice thing about radians. Another thing is, radians are often and very conveniently presented as fractions involving pi. So we don't want to reach for our calculator and actually get the decimal value here. This is much more valuable as a fraction involving pi, like 3 pi over 5. This tells us a few things. One is it tells us what fraction of a semicircle this angle is. We know that pi radians is exactly 180 degrees. So an angle of 3 pi over 5 radians would be about 3/5 of the way around. That's 3/5 of pi. Okay, and this also agrees with 108 degrees. Now let's do the next conversion. So negative 135 multiplied by pi divided by 180. This is also going to give us a fraction involving pi, and it'll be negative. 135 is 3/45, and 180 is 4/45, so this is negative 3 pi over 4. So we can visualize this as negative 3/4 of a semicircle. So negative angles, of course, reading clockwise. This is about negative 3/4 of the way around. So there's our angle of negative 3 pi over 4. All right, let's do this one. So 325.7 times pi divided by 180. Because they gave us this one in decimals, that's kind of a free license to use a calculator and give our answer in terms of decimals. So this is one occasion where we should just use our calculator. I get 5.684537374, and that's in radians. Well, we should probably round to the precision given in the problem. So this is 4 significant figures. So let's round this guy to 4 significant figures, 5.685 radians. And again, writing the word radian or rad is optional, although sometimes it's helpful to make the context clear. Okay, in this example we have some radian angles and we want to convert them to degrees. So to do that, we need to multiply by 180 and divide by pi. So for the radian angle 11 pi over 12, we are just going to multiply by 180 degrees, divide by pi. course, here the pi's simply cancel. All right, so 180 over 12 is 15. 15 times 11 is 165. So this is 165 degrees. For the next one, we have negative 7 pi over 6, and we're going to multiply by 180 degrees and divide by pi. So of course the pi's cancel, and 180 over 6 is 30, and negative 7 times 30 is negative 210 degrees. Okay, and just like the part C from the last example, if you are given a decimal value, that is free license to just use your calculator and give a decimal answer. So of course the calculation is the same. We're going to take the negative 2.92 radians. We will multiply by 180 degrees and divide by pi. And I get on the calculator negative 167.3036762 degrees. But let's round that to the nearest degree because we have 3 significant figures in the initial value. So that would be negative 167 degrees. And there we are. Okay, let's spend some time visiting our favorite angles, the special angles. So those are the ones that we would find in a special triangle, as well as the angles coterminal to those, and all the quadrantal angles too. So let's list them in degrees here first. So I guess our first special angle would just be the angle of 0 degrees. And over here we'll make a column for radians. And 0 degrees multiplied by pi divided by 180 would be 0 radians. All right, what's next? The next special angle is probably the 30-degree angle. And if we multiplied by pi and divided by 180, we would see that this reduces to a radian angle of pi over 6. Okay, next special angle we encounter is probably the 45 degree. And again, if we multiply by pi and divide by 180, that fraction reduces to simply pi over 4. Okay, next special angle we encounter is probably the 60-degree angle. And if we multiply 60 degrees by pi and divide by 180, that fraction reduces to pi over 3. All right, then we come up to our next quadrantal angle, which is 90 degrees. And if we went 90 degrees times pi divided by 180, we would see 90 over 180 is just 1/2. So this is pi over 2. All right. Let's skip to the next quadrantal value, which is 180 degrees, and we know that that's pi radians. Then there's the next quadrantal value of 270 degrees. So we know 270 degrees is 3 times 90. So that means that its radian value will be 3 times pi over 2, or 3 pi over 2. Now, of course, you could also just obtain that by simplifying this fraction, and you would get 3 pi over 2 from that. All right, let's skip to 360 degrees, which of course was our original exchange value between degrees and radians. We know that's 2 pi radians. Okay, these special angles are particularly useful to know without having to stop and convert, especially like the 30, the 45, the 60, knowing that 30 degrees is pi over 6, 45 degrees pi over 4, 60 degrees is pi over 3, and 90 degrees is pi over 2. That is very useful to know as immediate information. Let's see how that is actually useful. So if we want to do some conversions here, let's take a look at, say, 5 pi over 3. Now, one thing you could do, if you wanted to convert this to degrees, is go, well, that's 5 pi over 3 times 180 divided by pi, like we were doing in earlier examples, and work out that fraction. But if we know the special angles, we can do this very quickly. Because, of course, 5 pi over 3 is really 5 times pi over 3. And if you know pi over 3 is 60 degrees, then this is really 5 times 60 degrees, which is 300 degrees. All right, what about this one? Negative 3 pi over 4. Again, we would just say, well, that's negative 3 times whatever pi over 4 is. Okay, but pi over 4 is 45 degrees. So this is negative 3 times 45 degrees, or negative 135 degrees. Here's another wonderful thing about radians. You get reference angles for free. If you were handed 300 degrees and said, find the reference angle for 300 degrees, well, what would you have to do? You would draw 300 degrees right about here, as it is. And you would note that that's in the 4th quadrant, and there's its reference angle, which would be 60 degrees, because 360 minus 300 is 60. However, if you had that angle in radians, its reference angle is just this guy, pi over 3. Well, that is 60 degrees. So now I could immediately ask you, what's the reference angle for negative 3 pi over 4? Well, the answer is pi over 4, which is 45 degrees. Well, let's see how we can use radians to evaluate trig function values. All right, well, let's evaluate cosine of pi over 6. Now, until we learn the unit circle, which will be in this chapter, for now we should just convert everything to degrees. So let's convert pi over 6 to degrees. Okay, well, that means we're interested in cosine of pi over 6, which is 30 degrees. So, of course, it'd be convenient if you knew that off the top of your head, but of course you can always convert by multiplying by 180, dividing by pi. You'll see the pi's cancel. You'll get 180 over 6, which is 30. So what's cosine of 30 degrees? We can pull that off of one of our special triangles. So cosine of 30 degrees would be adjacent over hypotenuse, so that's rad 3 over 2. And that means that cosine of pi over 6 radians is rad 3 over 2. Now let's do another one. Okay, once again, we're going to convert this guy to degrees. So 5 pi over 6 is like 5 pi over 6's. So that's 5 30 degrees, which is 150 degrees. So this is like asking, what is the cosine of 150 degrees? All right, well, now we're going to need a reference angle. So 150 degrees is in the 2nd quadrant, and its reference angle would be 180 minus 150, which is 30 degrees. Okay, but we could have predicted that when we were converting this thing over, because pi over 6 is 30 degrees. Okay, so we know that because 150 degrees is in the 2nd quadrant, that its cosine value will be negative because only sine and cosecant are positive in the 2nd quadrant, and that the actual magnitude of our answer will be found by taking the cosine of the reference angle off of the special triangle. So cosine of 30 degrees is, of course, rad 3 over 2. So cosine of 5 pi over 6, which is, of course, cosine of 150 degrees, is negative rad 3 over 2. All right, let's evaluate cotangent of 3 pi over 4. So again, we'll just convert to degrees. 3 pi over 4 is 3 copies of whatever pi over 4 is, and we know pi over 4 is 45 degrees. So this is like 3 45 degrees. That's 135 degrees. So this is like asking, what is the cotangent of 135 degrees? Well, we're of course again going to need the quadrant and the reference angle here. Well, we know that 135 degrees is in the second quadrant, and so its reference angle is 180 minus 135, so that would be 45 degrees. But of course, we could have predicted that simply by looking at this stage of the conversion and noting that this is the reference angle right here, 45 degrees. Well, that means we're going to need to evaluate this using a 45, 45, 90 special triangle. All right, well, in the second quadrant, only sine and cosecant are positive, which means the cotangent value here will be negative. And looking at our triangle, we know that cotangent is the reciprocal of tangent. So we figure out what tangent of 45 degrees is, and then we take the reciprocal of that. Tangent is opposite over adjacent, which means cotangent would be adjacent over opposite. Well, in either case here, it'd be 1 over 1. So our cotangent of 135 degrees is -1, which means that the original problem, cotangent of 3 pi over 4, is -1. All right, let's do secant of 5 pi over 2. So as usual, we will convert to degrees. So 5 pi over 2 is 5 copies of whatever pi over 2 is, and that's 90 degrees. So 5 90s is 450 degrees. So secant of 5 pi over 2 is like secant of 450 degrees. Okay, well, this is a quadrantal angle. It's a multiple of 90 degrees. So it's not going to have a reference angle, and we can't answer this question by reading it off of a triangle. So for the quadrantal angles, we have to go back to our roots here and draw the quadrants and locate 450 degrees, which is right here. That would be 90, 180, 270, 360, and then 450 is one more 90. There we are. But notice that with the radians, it's even easier to count, because if you know that pi over 2 is 90 degrees, we have pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and 5 pi over 2. So you just kind of count 5 of those, and you've got where you land, which is right here. So let's pick a point on there. Call it 0, 1. So we have x is equal to 0, y is equal to 1, and we would calculate r, which will of course just be 1. So secant of 450 is r over x by definition, so that would be 1 over 0. Uh-oh. Oh no. Undefined. So after all that, secant of 450 degrees is undefined, and therefore secant of 5 pi over 2 radians is undefined. All right, so that's that.